Hello. Give it just a couple more minutes, make sure everybody's able to get logged in.
Do you think Kimberly in the waiting room?
She is coming in.
Oh, there she is.
There she is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Almost. Let's see, where am I? Let's see, we got Kinsley and Edelyn. We got Claire. We got Mark and Grant. We don't have Richard yet, do we? Let's see, Richard. We've got the King sisters. We've got Zoe Watley, but not Zoe Owens. We got Katy Perry, got Jonas, we got Sadie, and Micah. So it looks like we're missing Zoe Owens and Richard. So hopefully they'll log in just a minute. Okay, so what we're going to do is we are going to start off with checking our homework. So let's go ahead and open up to lesson 5 on page 11. I think that's where we need to be. Lesson 5, page 11. We had the right-hand column of activities 2. I'll put my glasses on so I can see these little bitty print in my book. Okay. So activities 2, page 11, left-hand column. Everybody ready? I'm just going to go down the list and call out the answers. When I get finished, if there's any of them that I need to work for you, let me know. Okay, so the first one, the absolute value of negative 29 plus the absolute value of 6 equals 35. The absolute value of 5 minus the absolute value of negative 24 equals negative 19. The opposite of the absolute value of 9 plus the absolute value of negative 13 equals 4. The opposite of the opposite of the absolute value of 1 minus the absolute value of negative 28 equals negative 29. The absolute value of 26 minus the absolute value of 35 equals negative 9. The opposite of the absolute value of negative 12 minus the absolute value of negative 15 equals negative 27. The absolute value of 19 plus 18 plus the absolute value of 23 minus 17 equals 43. The opposite of the absolute value of 24 minus 16 plus the absolute value of 15 minus 17 equals negative 6. And the opposite of the absolute value of 26 plus 14 minus the absolute value of 42 minus 18 equals negative 64. Any questions on any of those? Any of them that you missed and you would like me to go over them?
What was the very first one?
The very first one was 35. Let's see if I can get my screen to come up. And that way we'll have it just in case we need it. There we go. All right, and then in activities 3, we had the left-hand column. And get it where I can see everybody. All righty. Okay, left-hand column, activities 3. Positives and negatives. Positive 7, oh, here comes Richard. Positive 7 plus positive 15 is positive 22. Negative 13 plus positive 4 is negative 9. Negative 18 minus a negative 6 is negative 12. Positive 17 plus negative 65 is negative 48. Positive 29 plus positive 19 is positive 48. Positive 34 minus a negative 16 is positive 50. Any questions on those?
I got the second one wrong.
Okay.
And the very last one wrong.
Okay, so let's take a look at the second one, negative 13 plus a positive 4. Okay, so we take the sign of the larger value. Since the 13 is negative, I know it's going to be a negative answer. And the difference of 13 and 4, 13 minus 4 is 9. So negative 9. And then what was the other one?
The very last one.
The very last one. I've got a positive 34 minus a negative 16. Remember, when I'm subtracting, I want to change to adding the opposite. So if I make my subtraction sign an addition sign, that means I have to change the sign of negative 16 and it becomes positive 16. So then I have a positive 34 plus a positive 16, which would be a positive 50. Okay, so if you have subtraction, change it to addition, and then take the opposite sign of the number that follows. Any other questions on activities 3? All righty. Then our next assignment was activities 4 on page 12. So page 12, activities 4, we were doing prime factorization of our numbers and we were using exponents where appropriate. So our prime factorization for 27 was 3 times 3 times 3. So I would write that as 3 to the third power. 28 was 2 times 2 times 7. So that should be 2 squared times 7. 30, prime factorization would be 2 times 3 times 5. Nothing to express as exponents there. Next row, 32 would be expressed as 2 times 2 times 2 times 2 times 2, which would be expressed as 2 to the fifth power. 33 would be 3 times 11. And 35 is 5 times 7. Any questions on those? All righty. Make sure, let me look at my list and make sure Zoe Owens isn't waiting. Oop, what did I do? That's not what I want to do. I just want to move it. Okay. All righty. And then we had activities 5, the bottom 6 problems. Here she comes. Okay, so on what page did I say? Activities 5, the bottom 6 problems. Okay, so let me count down. Actually, there they are right here. All righty. So those of you that joined in a little bit late at the break, if you want to hang out for a minute and we can get you caught up on checking your homework answers that we're checking right now. Right now we are on page 12, activities 5. We're getting ready to check those last 6 problems. So the first one is 7 minus 3 to the second power minus 20 divided by 4. And that one, your solution is 11. Again, I'll go through the answers first, and then if you have questions at the end, we'll go through them and I can work any of these that you need me to work. So the answer for that one was 11. The next one, 4 plus 3 minus 2 squared plus 6 times 2. The solution is 15. Below that, 11 minus 8 to the third power minus 5 squared plus 7 times 2. Your solution is 16. Beneath that, 3 cubed divided by 9 plus 5 plus 1 minus 4. Your solution is 5. Then we have 2 times 8 minus 21 minus 16 plus 1 divided by 6, and your solution is 2. And then the last one, 2 plus 4 times 3 divided by 7 to the second power equals 4. Any of these that you would like me to work?
What's the fourth one?
Sorry, say that again, the third one?
The fourth.
The fourth one? Okay, so let's see, 1, 2, 3, 4, the 3 cubed divided by 9, the solution is 5.
Okay.
You need me to work that one?
No, ma'am.
Okay. Any other questions or any that you would want me to work?
Could you do the third one?
The third one? Sure. Okay. All right, so I've got my screen up, so we'll take a look at this one. All right, I have 11 minus 8 cubed minus 5 squared plus 7 times 2. So thinking about order of operations, PEMDAS, first thing I'm going to do is start with parentheses. So I'm starting with 11 minus 8. And 11 minus 8 is 3. So now I've got 3 cubed minus 5 squared plus 7 times 2. Okay? So I'm going to do my exponents, and in this step, I can go ahead and take care of both of these exponents at the same time. 3 squared is going to be 3 times 3. No, that's not squared. That's supposed to be cubed. Let me fix that. Sorry. Hey, and one of the things, I can't remember if I've told you guys or not, if y'all see that I've made a mistake, call me on it. If I mess something up, earlier I was doing a problem and I was borrowing from 9 or from 8 and I made it a 9 instead of making it a 7. So anyway, so I make all kinds of mistakes. Y'all know that. So call me on it if you see something that I've messed up on. That's supposed to be 3 cubed. Okay, so 3 cubed is 27 because 3 times 3 is 9 and 9 times 3 is 27. Minus 5 squared, 5 times 5 is 25, plus 7 times 2. Okay, now I have subtraction, addition, and multiplication. According to my order of operations, I'm going to have to multiply first. So I'm going to have 27 minus 25 plus 7 times 2 is 14. Okay. I have subtraction and addition and subtraction. So I know that my rule is when I have both in the same problem, I'm going to go from left to right. So I'm going to start with 27 minus 25 is 2, and 2 plus 14 equals 16. Any questions on that one or any others?
No, ma'am. Thank you.
Okay, you're welcome. All right. Nothing else? Then we had lesson 6, page 14. We said to finish activities 2 and activities 3. So let's take a look at that. Excuse me. So page 14. Lesson 6. Let's see, we're going to be at the bottom. Finish activities 2. This was dealing with our greatest common factor and least common multiple. Okay, so we're going to look at the greatest common factor. What we'll do is I will go down the middle column first. So I'll go top to bottom, middle column, then I'll move over to the right column, top to bottom in activities 2, and then we'll move on to activities 3. Okay, so for activities 2, the greatest common factor of 12 and 16 is 4. Below that, the greatest common factor of 16 and 20 is also 4. Below that, the greatest common factor of 16, 24, and 32 is 8. Any questions on any of those? All right, right-hand column. Greatest common factor of 15 and 35 is 5. The greatest common factor of 20 and 24 is 4. And the greatest common factor of 10, 18, and 30 is 2. Any questions on those? Everybody feel pretty comfortable with greatest common factor? All righty. Now we're going to go ahead and move on to activities 3, dealing with least common multiple. We'll do left-hand column first and then right-hand. Okay, least common multiple of 4 and 6 is going to be 12. The least common multiple of 12 and 15 is 60. The least common multiple of 10, 15, and 20 is also 60. Any questions on any of those? All right, right-hand column. Least common multiple of 9 and 12 is 36. Least common multiple of 12 and 16 is 48. Least common multiple of 9, 12, and 15 is 180. Any questions on any of those?
Can you repeat the first one?
The first one, the least common multiple of 9 and 12? It's 36.
Okay, thank you.
Uh-huh. Everybody good? All righty. Okay, so this was the end of the section for our test. Yay! So what we're going to do is I have put together a unit review, little study guide that we can go through and practice on. Let me pull it up real quick. So what I'm going to be doing is we're going to go through the sections, we're going to review, and then I'm going to be emailing this to you at the end of class, and this will be part of your homework assignment. So we have a Algebra 1, Unit 1 study guide. So what we'll do is so this will be due on Monday. On Monday, we will go through these answers, make sure everybody's good, and then your test will be emailed on Monday, okay? So we're gonna do some review right now. You'll have your unit review for homework. Monday, you'll get your test, and then you'll submit it next Thursday, okay? So let's go ahead and take a look at this. Like I said, I will email this to you for you to print out and go through. And this is your study guide. This is to help you prepare for the test, for you to know what each of these things are. I will tell you that at the first part of the test, it will be a matching section. And you'll be matching some of these vocabulary terms, some of these words that we've been learning to examples of what they represent. So you'll want to be sure to know when we talk about kinds of numbers, what are the different numbers that are within those sets, okay? So let's flip back for just a minute to lesson 1 on page 3. So you can see that on the study guide, number 1 deals with kinds of numbers. So you're going to be able to find this information on page 3 of your book, where we talked about natural numbers. We also call those counting numbers. That's the 1, 2, 3, 4, 5, 6, 7, 8, what you learned when you were little bitty. Our next thing is whole numbers. We've got the natural numbers and the number 0. Integers, positive and negative whole numbers. And then also part of the question about integers is talking about what is the thing that I told you to picture in your head when we're talking about integers, and what is that?
You see
A number line?
Number line, good. Picture your number line when you're talking about integers. Then we have rational numbers, numbers that can be written as a fraction. And did we talk about, if you look at the, remember we talked about another word for fraction is ratio? We talked about that? Ratio and fraction mean the same thing. And look at the first 1, 2, 3, 4, 5 letters of the word rational. The beginning of rational is ratio. So if you have trouble remembering, oh, rational expresses as a fraction, well, right here, I'll go ahead and highlight it. You can see that here, ratio is at the beginning of rational, and a ratio is the same as a fraction, okay? So rational, ratio, fraction, kind of put those things together. So if a rational number can be written as a fraction, then we know that an irrational number cannot be written as a fraction. Rational numbers and irrational numbers both involve decimals, but the main difference is that our irrational numbers, our decimals are non-repeating, non-terminating, like the symbol pi that we see. Also, imperfect square roots are going to be examples of irrational numbers, okay? And then we learned that the whole entire set of real numbers is what makes up all of these, and I don't even think I put anything on here about real numbers. All right, the second section, signed number rules, okay? So the whole, you can see I've put a lot of information on here about the rules about signed numbers, whether it's adding and subtracting or multiplying and dividing. That is also from lesson 1. We know that if we add and we have the same signs, we add 2 numbers with the same signs, our solution will be whatever that sign is. Adding opposites, keep the sign of the larger, take the difference. Multiplying and dividing, if I multiply 2 numbers together that are the same sign, I'm going to have a positive solution. Multiply opposites, I'm going to have a negative solution. And then, oh, and I forgot to mention with subtraction, changing to adding the opposite helps with subtraction. Okay, so all of that is going to be dealing with signed numbers. Moving on to lesson 2, we were dealing with exponents. Okay, so lesson 2 will correspond with number 3 on your study guide. We've learned that exponents tell us how many times to multiply a number by itself. The number that we are multiplying is called the base, and how many times we multiply it is the exponent. Any number to the 0 power is equal to 1. Any number to the first power is itself. If I'm multiplying like bases, I add the exponents. If I'm dividing like bases, I subtract the exponents. If I have two numbers, or if I have factors in parentheses with an exponent on the outside, I can distribute those exponents to the numbers, or I can multiply what's in parentheses first and then raise it to that power. And if I have a negative exponent, I know I'm going to have to take the reciprocal of the number. If the exponent is outside parentheses, I have to distribute it to both the numerator and the denominator. But if there are no parentheses, I keep the exponent with the number it was originally with. Okay? Those are our exponents. Lesson 3, order of operations, PEMDAS. It says to list the order of operations. And I put a little asterisk at the bottom that says if there is multiplication and division or addition and subtraction in the same problem, complete them in order from left to right. Okay, so that's going to be lesson 3. Lesson 4, factors. So this is actually going to cover numbers 5, 6, 7, 8, and 9. We've learned that factors are numbers that divide evenly into another number without a remainder. We also learned, or you can look at it as two numbers that multiply together to make another number. When we talk about prime numbers, numbers that are the only factors are 1 in itself. Composite numbers are all the other ones. We learned that our smallest prime factor is 2, and that is our only even prime factor. Prime factorization is the process of breaking a number down into prime factors. Okay. Lesson 5, absolute value. This is going to correspond with number 10 on the study guide. Excuse me. Absolute value. We talked about how absolute value is the distance from 0 on a number line, and that distance cannot be negative. So absolute value is always going to be positive unless there is a negative sign outside of the absolute value symbol. Okay, if there's a negative outside the absolute value sign, I read that as the opposite of the absolute value of whatever, so then I will have a negative answer. Okay. Greatest common factor, least common multiple, numbers 11 and 12, going to correspond with lesson 6. So I put the steps. So least common, I find the greatest common factor. I know that my first step for both of these is going to be prime factorization. Okay, list the prime factors. Second step for greatest common factor, this is where I look and I buddy up. I circle the common factors between both numbers or all 3 numbers, however many numbers. I'm looking to see what's in common for all of them. If I have more than one number in common, then step 3, I'm going to multiply those together to find the greatest common factor. Least common multiple, again, step 1, start by finding prime factors. Step 2 is different from greatest common multiple, greatest common factor, because here I want to make sure that every single factor that is listed between all of my numbers, I want to make sure that they are all represented. But if I have a 2 in one, but I have 2 to the second power in another one and 2 to the third power in the other one, I need to draw a box around the exponent that is the greatest. So I would put my box around 2 to the third power, so that represents my factor of 2. If I only had a 3 in one of my lists, I would still put a box around that 3 because I have to make sure to represent every single number that is listed. Okay? Then again, I multiply them together to find the least common multiple. Any questions about any of that? I know that was a super fast overview. Any questions though about any of those things that you're confused on?
Yeah, is this the study guide or the test?
Okay, this is the study guide. So this is something I will be emailing this out at the end of class. So that way you can print it. You're going to go through the book. This is kind of help you to study. And then that way, this is what you're going to look at and study before you take your test on Monday. Okay. Then the actual test will be application. Okay. The beginning part, like I said, will be matching to where it may say, you know, you're matching whole numbers to examples of whole numbers. You're matching, I don't know, any of the other terms that we've used, you know, prime factorization, breaking down a number into prime factors. You may be matching those vocabulary terms, but then there will be a part on the test where you're telling what the absolute value of a number is. You're doing some absolute value computation. You're doing prime factorization. You're doing least common multiples and stuff like that. So you'll actually be doing the math part of it. This is just kind of the steps and directions and things like that. Okay. So this is the study guide. This will be for homework and it will be due on Monday. Okay. All right. So I'm going to write that down first. So today is 8/20. So first part of homework is the study guide. Test will go home on Monday. All right, so what we're going to be doing today, we are moving on to our next unit of information, okay? So now what we're going to be doing is we are going to be moving on to lesson 7. It will actually not be covered until our next test, okay? So everything that was on the study guide, last thing that'll be on the test is least common multiple. We're starting lesson 7 today, which is dealing with roots and radicals. This will not be on the test on Monday. This is our new section. Okay, everybody good with that? All righty, so we learned about exponents, okay? We've learned about when we look at a number and we have an exponent, and that means I'm going to multiply something by that many times, okay? And so now what we're doing is we're kind of doing the opposite of that. Okay, so on page 15, no, come on, expand. Okay, so on page 15 at the top, it says the opposite of raising a number to an exponent is taking the root of a number. Okay, so when we talk about taking roots, we're going to use the symbol, which is called a radical. Okay, so if you hear me say the word radical in your head, I want you to picture this square root symbol. Okay, we call it a square root symbol. The real name is radical because in a minute we're going to look at, well, what happens if I have another number there? What if I have a number listed instead of it just being blank? Okay, so when I say the word radical, if I say something about write the number under the radical, this is what I'm talking about, is this little symbol, okay? The number under the radical is called the radicand or the argument. I'll be calling it the radicand. So if we look at this one right here, 16 is under the radical, and so that is called the radicand, okay? The number that indicates the root is called the index. Okay, so what I'm going to do now is I want to talk about the index for a minute. If I have a symbol that looks like this, and I had 16 under it, okay, notice that I do not have a number written here. If there is no number written there, I understand that number to be a 2. Okay, so when we talk about a square root, I understand that number to be a 2. Nothing there. If it is blank, I understand it is a 2. So that means that when I list the prime factors of 16, I start with 16 and I say, what is my smallest prime factor? That is 2, and that would be 2 times 8. 8, smallest prime factor is 2, and that's going to be 2 times 4. 4, smallest prime factor is 2, and that's going to be 2 times 2. Okay? Again, I can check. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. That index there tells me that I need 2 buddies to come out as whole numbers. So if I circle 2 2s, that means I can bring out 2 2s and multiply them together and get my whole number. Don't stress about this too much. We're going to cover this in a much slower pace in just a minute. I'm just trying to show you the difference. Now, if I were to have the cubed root of 16, notice I have put a different number here. Okay, earlier I had no number. I understood it to be 2. So that told me I have to have 2 buddies. If I did the same thing here and I've got the cubed root of, and I do my prime factors of 16 where I've got 2 times 2 times 2 times 2, same prime factors, but here I have to have 3 buddies for one whole 2 to come out. So then this would equal 2 to the cubed root of 2, because I would have to have 3 of them for one whole number to come out. This guy's left by himself because he doesn't have anybody, so he has to stay under the radicand. That is the difference. That's what the difference the index makes. The index tells you how many buddies have to be under the radicand for a whole number to come out. Does that make sense? And I will tell you, buddies is not a mathematical term. That is a Jennifer Fountain term. It's just the best way that I've been able to come up with, you know, trying to find the best way. But it just seems to work for me. So if you have a better idea, a better suggestion, please let me know. Because I know it sounds silly, and that's what I was trying to do with math with my son this summer, because for him, the math program he was going into, we had to do a whole textbook of math this summer. That was exciting. So as we were doing that, and I'm talking about buddies, he was like, Mom, that is the stupidest thing I've ever heard. And I'm like, just work with me, kid. So anyway, I know that some of the things I say is silly, but hopefully it'll kind of help you remember. Okay, so my index tells me my number of buddies. All right. We'll keep on going here.
Wait, it tells you how many buddies do what?
So do you notice that, and like I said, we're going to go more in depth in this. Do you see how when I listed my prime factors and when my index was 2, I had to circle 2 of my same factors for them to come out as one whole number. So basically I said, if 2 times 2 is 4, so the square root of 4 is 2, and the square root of this 4 would be 2. So I was able to pull out 2 times 2 is 4. Okay, so it tells how many of the numbers under the radicand I have to circle for one whole one to come out. But when my index was 3, I had to circle 3 2s for one whole number 2 to come out. Okay, and then the little guy that was left behind that didn't have a buddy, he had to stay under the radicand. He has to stay in the house. Mama won't let him go out by himself. You gotta go out with buddies. Okay, so it says, for example, 2 cubed equals 8. Okay, we know that 2 cubed is 2 times 2 times 2, and that equals 8. So to express this as a root, you would have the cubed root of 8 equals 2. I would need to make 3. I have to multiply 2 3 times to equal 8. So 8 is the radicand, 3 is the index, and 2 is the root. In this case, 2 is the cube root of 8. Because again, I would have the cubed root of 8 is equal to 2 times 2 times 2, because my index is 3 I have to have 3 of the same number for my whole number to come out as a 2. Okay? So it says to find the square root of a number, find a number that when multiplied by itself gives the radicand. So if I'm doing the square root of 16, I think what times itself is 16? And that's 4. Again, if I do not know that, I can go with the same route I've been doing where I have the square root of 16, which would be 2 times 2 times 2 times 2. I circle my buddies. That means 2 2's come out, and 2 times 2 is 4. Okay? So if I do not know perfect squares, I can always break it down using prime factorization. So look at the next one. For larger numbers, write the radicand as the product of perfect square factors and then find the square roots. So again, to be able to do that, I have to know perfect squares. If you have not memorized perfect squares, then that's not going to help you much, okay? So let's look at what I would do for the square root of 128. Let me find a little space. Actually, what I'll do is I'll get a clean piece of paper. Okay. If I'm dealing with the square root of 128, to break down a radical, the first thing that I do is I want to identify the smallest prime factor of the radicand. Okay, so the first thing I do is I say, okay, what is my smallest prime factor of 128? So if it's even, I know my smallest prime factor is 2. Okay, if it's not an even number, then I would start with 3. So since I know that my smallest prime factor, that's going to be 2. Okay, so my step 2 is going to be to identify all prime factors of the radicand using the smallest primes first. So what I'm going to do here is this would be the same as, you know how we did our ladder? And so I would say, okay, 2 will go into 128. Well, 2 will go into 12 6 times, and 2 will go into 8 4 times. So 2 will go into 128 64 times. So then again, I'm going to look at my smallest prime factor. Smallest prime factor of 64 is going to be 2. Always going to try to start with 2 if my number's even. 2 will go into 64. 2 will go into 6 3 times, and it'll go into 4 2 times. Again, smallest prime factor will be 2. 2 into 32. Half of 32 is going to be 16. 2 will go into 16 8 times. 2 will go into 8
4 times.
4 times. 2 will go into 4 2 times, and 2 will go into 2 1 time. Okay, so here I can see that I have written this as 2 2 2 2 2 2 2. Okay, so I can see that now I can write underneath my radical, I've got 1 2 3 4 5 6 7 2's. So I have 2 times 2 times 2 times 2 times 2 times 2 times 2. 1 2 3 4 5 6 7. Again, I can check and make sure I didn't list too many or I listed enough. And 2 times 2 is 4. So 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. And 64 times 2 is 128. So I know I have enough 2's listed. All right, so we've identified all of our primes. Step 3, I have to look at the index to determine how many of each prime factor must be grouped together to come out from under the radical as a whole, as one whole number. Okay, so I've got to look at that index to determine how many I have to group together for it to come out as one whole number. Okay, so I'm going to look at that. So what is my index here? What is my index for the square root of 128? Remember, I'm looking to see what number is written right there. Do I have a number written there? There's nothing there, so I have to understand that it is a 2, okay? Because I know that if there's nothing there, it is the square root of 128. So that means I need 2 buddies. I need to pair up 2 2s. So I'm able to look at this and say, here's 1 group of 2s, 2 group of 2s, and 3 group of 2s. For every pair, only one whole number 2 can come out from under the radical, okay? So for each pair of 2s, I have one pair of 2s, I have another, and another, okay? So I'm able to pull out 3 2s. My other radical, and my other number, my other number that was not buddied up has to stay under the radicand. So remember I said they can come out from under the radical as one whole number if more than one whole number is, I'm going to say, buddied and comes out as a whole number. Multiply them together. So now what I'm going to do is I'm going to take whatever whole numbers came out and I multiply them together. So in this example, I have 2 times 2 times 2. 2 times 2 is 4, 4 times 2 is 8, and then I have the square root of 2 left under the radical because it could not be buddied. Okay? The first thing I did is I started listing my prime factors. If you need to use the ladder method, if you want to use your factor tree where you do 128 and you break it down, you've got 2 times 64, which is 2 times 32, and so forth. You can factor tree it, whatever you need to do, but what you've got to do is list it as prime factors, okay? So that's steps 1 and 2, we're listing prime factors. Now the next thing I need to do is look at my index to determine how many numbers I need to circle together, how many buddies I need to have, okay? Whatever groupings I'm able to put together, then I can pull out as a whole number. Whatever is not grouped has to stay under the radical, okay? So let's look at that for just a minute. I'm going to come down here, and we found that the square root of 128 equals 8 times the square root of 2. Let's look at how the cubed root of 128 would be different, okay? I'm not going to go through the whole thing that we just did. So I had 1, 2, 3, 4, 5, 6, 7 2s. So I would have the cubed root of 1, 2, 3, 4, 5, 6, 7. Remember, my index tells me that now I have to have 3 2's. Okay? So this group of 2's comes out as one whole number 2. This group of 2's comes out as another whole number of 2's. And then I have one little guy left under there that can't come out. So I've got to multiply those together. 2 times 2 is 4. So the cubed root of 128 is 4 times the cubed root of 2. Okay, so that index is what tells you how many of each thing you need to have. Okay, any questions about that? So, let me, Let me do.
Computer glitched out.
That's okay. I'm coming up with a problem real quick. 7 times 4, 8, 2. Okay, let's look at, we're going to compare the difference of the square root of 108 and the cubed root of 108. Okay. First thing I'm going to do is I'm going to list my prime factors. Okay. The number is 108. It is even, so I want to start with a 2. Again, when I am starting with that prime factor of 2, I'm basically doing the same thing as the ladder method. I'm just not writing it out. So at this point, if you're able to go more abstract and do it in your head, that is fine. If you need to write out the ladder method or you need to write out prime factorization with the factor tree, do what you've got to do, okay? Do what you've got to do if you need a more concrete way to do it. But as you start getting a little more used to it, it's going to be easier to do in your head, okay? So we've got about 4 more minutes before break, so don't let me miss break today. Okay, so we said we're starting with our smallest prime factor, which is 2. 2 will go into 108, 2 will go into 10, 5, and 2 will go into 8, 4, so that'll be 54. So I'm going to list my first prime factor of 2 is there. 2 will go into 54. Well, 2 will go into 50, that it's 25. So 2 will go into 54, what is that, 27? Okay, so I had another prime factor of 2. That's what I've got those right there. So now I've got 27. 27 is not even, so now I'm going to try 3. 3 will go into 27 9 times. So that's where I'm going to get that next 3. 3 will go into 9 3 times. So I'm going to write another 3 here. And then that is 3 times 1. So once I've gotten to my 1, I know I'm done. Okay? So the prime factorization for 108 is 2 times 2 times 3 times 3 times 3. All right. My index here is not written, so I understand that it is a 2. I have to have 2 of each thing. So I have 2 2's. I have 2 3's. So that means that these 2 2's come out as a whole number 2. These 3's come out as a whole number 3. I have a 3 left under the radical, so it has to stay there. And now I multiply 2 times 3 is 6 times the square root of 3. So there is my answer for 108 equals 6 times the square root of 3. Did everybody follow how I did that? Any questions on where I got any numbers, why I did what I did? All right, so that was dealing with square root. Let's look at how this is going to be different for cubed root. The cubed root of 108, we found that our prime factorization is 2 times 2 times 3 times 3 times 3. All right, my index is 3. That means I have to have 3 of something. Well, the only thing that I have 3 of are my 3 3s. So then that means that those 3s are going to come out as a whole number 3. But under my radical are those 2 2s. I didn't have another 2 to go with that one. So this time I'm going to have 3 times the cubed root of 4. I multiply those 2's back together and I've got 3 times the cubed root of 4. Does that make sense a little bit more about the index? Why the index is important? The index determines how many buddies I have to have, but remember that whatever that group of buddies is, I can only pull out one whole number for that entire group, okay? All righty, so let's go ahead and get back to our textbook on page 15. Let me pull that page back up. All right, so the next thing is talking about adding and subtracting roots. To add or subtract roots, the radicands and indexes must be equal. So when I look at the square root of 3 and the square root of 3, the indexes are the same. Neither are written, so I understand that they are 2. And my radicand is 3 in both of them, so they are identical. So when I have the square root of 3 plus the square root of 3, I'm thinking about what whole number is in front of each of these that is not written there, but again, I need to know it is there. Does anybody know what number would be in front of those?
1.
1. So the square root of 3 is the same as 1 times the square root of 3. Anything not times 1. Ooh, I bet I messed a brick, didn't I? Okay, I'm only a minute over. Okay, take a break, take a 5-minute break. We'll come back and pick up with this. Richard, were you okay logging in today? Did you have trouble?
Oh, I accidentally clicked the wrong link.
Oh no, I had somebody from the earlier class do that too, and that's what they were having trouble because they had clicked, I guess it was in geometry, so they had clicked the Wednesday link. Yes, and so unfortunately the links have to be separate for each day for it to be reoccurring. So there are 2 links. Sorry about that. do you want to go ahead and do you want me to call out the answers for you to check your homework real quick?
Sure.
Okay. Let's see. We started with let me see real quick. And then who else? I guess it was Zoe Owens. Okay, so the first one we had was lesson 5, activities 2, the right column. Lesson 5, activities 2, right column. Okay, you ready? Okay, so I'll just go down and read out those answers. So down that left column, the first one is 35. The next one is negative 19. Then I have positive 4, negative 29, negative 9, negative 27, positive 43, negative 6, and negative 64. Any of those you need me to repeat? Okay. Then activities 3, left-hand column, page 11. So activities 3, left column. I'll go down. The first one is positive 22. Then I have negative 9, negative 12, negative 48, positive 48, and positive 50. You good with those? Okay. Then we had page 12, activities 4. Okay, so we were dealing with prime factorization. So I'll go across the top row and then the bottom row. So the prime factorization for 27 was 3 cubed, or 3 to the 3rd power. Prime factorization for 28 was 2 squared times 7. 30 is 2 times 3 times 5. Bottom row, 32 is 2 to the 5th power. 33 is 3 times 11. And 35 is 5 times 7. Any questions on those? All righty, and then we had the bottom 6 problems of activities 5. So 1, 2, 3, 4, 5, 6. So starting with the 7 minus 3 squared, that answer was 11. The one below that is 15. Below that is 16. Then I had 5, 2, and then 4. Any questions on any of those?
No, ma'am.
All right, and then did you get lesson 6, page 14? Were you tuned in when we checked those, or do I need to do those?
I was tuned in for that.
Okay,
I think I joined right as you started that.
Okay, perfect. So I just want to make sure you were able to check everything. Zoe, were there any homework things that I needed to go over for you, hun?
Yes. Could you go over the activities to the column you made us do for homework? Because I only got one of those that I heard you say.
Okay, on page 11.
Yes.
All right, page 11, activities to the right-hand column. Positive 35, negative 19, positive 4, negative 29, negative 9, negative 27, positive 43, negative 6, negative 64. Any questions on any of those? And then activities 3, left-hand column, did you get those?
Oh, I got those, yes.
Okay, perfect. I couldn't remember at what point you were able to tune in. So, okay, good. I think everybody should be caught up.
So, do we have any homework in lesson 7 or no?
So we will have homework for lesson 7. We'll just wait and see how far we're going to get with it, because we'll do some of it as practice and then some of it we'll have for homework. So as of right now, the only homework we've talked about is the study guide. Oh, Sadie. I guess Sadie's having trouble. Oh, here she comes. Did you get back in, Sadie? There's Sadie. Okay, so let's get back to it. Micah, Jonas, Mark, is everybody there? Kinsley?
Yes, ma'am, I'm here.
Okay, just wanted to make sure everybody was there. Jonas, did you say yeah?
Yeah.
Okay, perfect.
My camera on this computer isn't working.
That's
So
fine.
turn it off.
That's fine. All righty, just want to make sure everybody was back before I got started. Okay, so we just left off where we were talking about if I have a problem where I'm adding square roots or cubed roots, or we could even have fourth roots or 100th roots, whatever that little number is, that index that goes above the radical sign. As long as the index and the radicand is the same, then I can add them together. And like I said, if there is not a number in front of the radical sign, I understand that to be a 1. Okay, so that's what we had just looked at here, where if I have the square root of 3 plus the square root of 3, I understand that's the same as 1 times the square root of 3 plus 1 times the square root of 3. So now what I can do is I'm going to add 1 plus 1, and then I keep the radical, which is the square root of 3, which is the same. So that's going to be 2 times the square root of 3. Okay? So if there is not a number in front of it, I understand that it is a 1, and I just add them together. Okay? So that's where we ended up with the 2 times the square root of 3. So if we look at this next one here, I have numbers written in front of the radical. I have a 2 and a 4. 2 plus 4 is 6. But then I keep my radical the same, okay? All I have to do is add the numbers in front of the radicals and then keep the radical the same. That is when I am adding or subtracting, okay? The main things with that, though, is the index and the radicand has to be exactly the same. Then it says to multiply or divide roots with the same index, or multiply or divide the radicands and write the answer under one radical. So on this one, my radicands do not have to be the same. They can be totally different. So you can see in this example here, I have the square root of 12 times the square root of 3. I'm going to write those together underneath the same radical. So in this one, the square root of 12 times the square root of 3 becomes the square root of 36, because 12 times 3 is 36. Now, if these did not multiply together to make a perfect square, in this step right here, I could break down 12 as 2 times 2 times 3, and then I've got my 3 right there. So what I did here is I broke down 2 into prime factors. Okay, so if I did not know that the square root of 36 was 6, again, I would just break down into prime factors. I know that I'm going to have buddies. I've got to have 2 buddies. So then I'm able to bring those out and have 2 times 3, which is 6. It helps to know your perfect squares. If you haven't memorized perfect squares, that can be something, kind of do flashcards. 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, and keep on going. I would go at least until 13, maybe even 14, okay? So if you learn your perfect squares, then that's going to help you in the long run. Okay, so really quick, to simplify radicals, I'm listing prime factors, I'm doing my buddy thing, and then I'm finding my answer. I have to pay attention to my index to determine my number of buddies. If I am adding radicals, my index and radicands have to be the same. I add my numbers in front of the radicals together and keep my radical. If I'm multiplying radicals, I go ahead and put them underneath the same radical sign. I simplify into prime factors and then deal with my buddies and simplify. Okay, so let's practice with this a little bit. We're in classwork 1. It says rewrite the following expressions as roots. So basically what it's doing here is it's saying 2 to the 4th power equals 16. So if I wanted to write this as the expression of roots, what I want to do here is I would say, excuse me, I would go ahead and write this as 2 equals the 4th root of 16. Okay. This one would be written as 3 equals the square root.
Is the 4 the index?
4 ends up becoming the index, yes. So the exponent becomes the index. Okay. My base is my solution, and that becomes my radicand. Okay, so 3 to the 2nd power equals 9. I would break that into 3 equals the square root of 9. Remember, if my index is 2, I don't have to write it. Same thing here, where 5 would equal the square root of 25. Or 5 equals the cubed root of 125. And 6 equals the cubed root of 216. That's just to kind of help you understand and see how these things are related. We really won't have any work associated with, we'll have a little bit, I guess, in activities 2, but that's not a major skill that we'll be working on. All right, so here, solve the following roots. If I knew perfect squares, I would know that what is the square root of 16?
4.
4. If I did not know that, then what I would have to do is I would start with 16 and I'd have to list my prime factors. 16 is going to be 2 times 8. 8 will break down into 2 times 4. 4 will break down into 2 times 2. Okay? I've got buddies here, buddies here. That comes out as 2 times 2, which is 4. I can either break it down, or if I already know that the square root of 16 is 4, then I've got my answer immediately. All right, the cubed root of 27. If I know the cubed root of 27, I could answer this immediately. Does anybody know the cubed root of 27?
9.
9?
No. Okay, let's take a look at it. Let's break it down. The cubed root of 27. 27 is not even, so I know that I cannot start with 2. I'm going to start with 3. 3 times 9 is 27, so 9 breaks down into 3 times 3. How many buddies do I have to have if I have a cubed root? I've got to have 3 buddies. Those 3 buddies come out as one whole number 3. So the cubed root of 27 is 3, because 3 times 3 times 3 equals 27. All right, let's look at 32. The square root of 32. What is the smallest prime factor I'm going to try with 32?
2.
Good, 2. And 32 is 2 times 16. Now I'm going to break down 16. That is 2 times 8. 8 is 2 times 4. 4 is 2 times 2. Okay. So now, how many buddies do I need? 2 buddies. I've got 2 buddies there, and I've got 2 buddies there. So those buddies are able to come out. So I've got 1 group of 2, 2 groups of 2. Poor little guy ends up being left under the radical. So 2 times 2 is 4 times the square root of 2. At any point that we are going through this and you do not understand why I'm doing what I'm doing, please stop me, okay? Please don't hesitate to ask. Simplifying radicals is going to be a skill that you are going to see from here on out, okay? So it's important that you understand what radicals are. It's important that you get comfortable with them and that you're not intimidated by them. I know a lot of times when we see something new, we see something different, it's real easy to get overwhelmed by it. But that's why I'm wanting to take time right now to go very slow through it to make sure you understand, because this textbook uses radicals a lot. Okay, you will see a lot of problems as we go through that deals with square roots. So you need, it's better for us to take the time to work on it now and for you to understand it really well before we get into where we're trying to figure out a different concept, but now we're having to go back and relearn simplifying radicals. Okay. Alrighty, now we're doing the cubed root of 16. So the cubed root of 16, we said that 16 will be 2 times 2 times 2 times 2, because 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. My index is 3. So I've got to have 3 buddies for one whole number to come out. So I'm able to bring out one whole number 2. I have a square root of, I have a cubed root of 2 left over that can't come out from under the radical. Okay. So that's simplifying. Now what we're going to do is we are going to look at adding. First thing I have to ask myself, are the indexes the same, or really they're called indices, but is my index the same for each of them, and are they the same radicand? Index is both 2, radicand is 2, so I can add these. Remember, if you want to write in front of it that 1, so you don't forget, if there is nothing written in front of it, I understand that it is a 1, so I can write that in front of it. So then I have 1 plus 1 is 2. Then I keep my radical the same. The next one, I don't have anything in,
I have a question.
What's that?
So on the last problem, the square root of 16.
The cubed root of 16, where our index is 3,
How come the 3 2's are 3 cubed instead of 6? No, 8. How come it's 3 cubed instead of 8?
Okay, because what happens is when I'm looking at the cubed root of 8, okay, when it's 2 times 2 times 2, those 3 buddies have to be together to come out of as one group. And the reason that is because if I have, so I'm gonna come over here for just a minute. Like if I had 2 cubed equals 8, right? You remember when we did this up here? When we were working with these up here? And if I had 2 cubed equals 8, then I would write that, I would take this 2 equals the cubed root of 8. Okay, and the reason that is because it takes 3 2's to equal 8. So when they come out from under the radical, whatever I have circled as one group, it only comes out as one of that number. Okay, so because on that one, 3 2's together only come out as 1 2.
Why is there a 3 under the radical?
Oh, because I messed up. and it's supposed to be a 2. Thank you.
Okay, I got worried. I was like,
No.
wait.
Like I said, when I mess up, y'all know that my hand will write faster than my brain is working a lot of times, and I write something totally wrong. So thank you. Because then other people, if you're confused, other people are too, and they're going, ooh, that's, again, it's not magic. I just made a mistake. So thank you for mentioning that. Does that help, Richard?
Yes, ma'am.
Okay, so that's why I make a big deal about circling the buddies. So whatever I have circled can only come out as one group of that number. So it only comes out as one of that number, okay? All right, so we added the 1 times the square root of 2 plus 1 times the square root of 2 and got 2 times the square root of 2. Here, I do not have a number in front of the square root of 5, so I'm gonna go ahead and write that 1 so I don't forget to add it. So I'm gonna add 1 plus 2 is 3. And then I keep my radical the same. So 1 square root of 5 plus 2 square root of 5 equals 3 square root of 5. And one of the things I want to mention, when I have 3 square root of 5, that operation in between is multiplication. 3 times the square root of 5, okay? Now let's look at the next one. I have the cubed root of 10 plus 5 times the cubed root of 10. Again, this would be a 1. 1 plus 5 is 6, and then I would keep the cubed root of 10. Any questions? 6 times the square root of 7 minus 4 times the square root of 7. My index and radicands are the same. 6 minus 4 is 2 times the square root of 7. Same thing with the next one. Index and radicands are the same. So 5 minus 4 is 1 times the cubed root of 5. I can simplify that by just writing the cubed root of 5 as my solution. If you want to keep the 1 there, that's fine. It does not make it wrong, okay? You can keep it or you can get rid of it. It's up to you. So that's addition and subtraction. Now let's look at multiplication. Remember, when I'm multiplying my radicals, they do not have to be the same, and I'm going to combine them under the same radical sign. So I have 10 times 2. If I were to multiply these together, 10 times 2 is 20, and there is not a perfect square of 20. So what I want to do before I even multiply them together is I want to go ahead and list these as prime factors. So let's think about 10. My smallest prime factor of 10 is going to be 2, and that will be 2 times 5, right? So I have broken 10 into 2 times 5. I cannot forget this 2 that is also under here, so now I have to multiply by 2 as well. Okay, so 10 times 2 has become 2 times 5 times 2. Is everybody with me on that so far? All right, my index is 2, so that means I need my 2 buddies. So they're separated right now, so I'm just going to go ahead and circle them independently. I have 2 2s that are circled, so that means that those 2 2s come out as a whole group of 2s, or a whole number 2. My 5 does not have a buddy, so he has to stay under the radical.
What would happen if you didn't break them up?
If you would have left this, so if you would have multiplied and you had the square root of 20, number one, if you don't simplify, then you will get counted off. I will not mark it wrong, but I will count off. If you multiplied them first and then you simplified, you would say the smallest prime factor of 20 is 2, and that's 2 times 10. 10 is 2 times 5. You've got 2 2s, bring it out, 2 square root of 5. So if you multiplied them together and then did prime factors, you're still going to get the same answer. I just find it easier to break down 10 instead of 20. It's going to be less steps to break down a smaller number, but you're still going to get the same answer, okay? So we could either go ahead and multiply them together, get 20, and then simplify, or I can go ahead and simplify each individual factor. Does that make sense? Does that answer your question, Zoe?
Yeah.
Okay. All righty. Now the next one, I have 3 times the square root of 5 times 2 times the square root of 2. All right, so the first thing I've got to do is I've got to multiply 3 times 2. All right, so I'm going to multiply 3 times 2. Then under my radical sign, I'm going to put 5 times 2 because they're both under the radicals. My 3 and my 2 are whole numbers outside of my radical, so I keep them outside the radical. What is underneath my radicals, square root of 5, square root of 2, are going to go together underneath my radical. Is everybody good with that so far? Now I'm going to simplify. 3 times 2 is 6. I cannot break down 5 and 2 anymore, so I'm going to go ahead and just multiply them back together and have the square root of 10. And that would be my answer. Any questions on that? All righty. Now we're going to divide. Division, same thing like multiplication, except for now I'm going to put this under the radical. Instead of multiplying them, I'm going to have 27 divided by 3 under the radical. What is 27 divided by 3?
9.
9. What is the square root of 9? If I don't know, yeah, I see Evelyn. Evelyn says 3. If I didn't know what the square root of 9 was, I could break that down into 3 times 3. And so there would be my buddies, and I'd pull out a whole number 3. Okay, so if I'm dividing, I put my division problem under the radical. 27 divided by 3 is 9. Simplify the square root of 9, and that's 3. Now, if I have numbers in front of my radicals and I'm dividing, I'm going to start with 10 divided by 5. So I'll have 10 divided by 5. But now I'm going to have times the cubed root of, and I'm going to put 16 divided by 4. Okay, so I'm taking the first part of each problem and dividing them, and then I'm putting the radicals together to divide them. All right, and 10 divided by 5 equals 2 times the cubed root of 16 divided by 4 is 4. I know that 4 is 2 times 2, so I could not get 3 buddies out of that, so I cannot simplify the cubed root of 4. That's as simple as it will go. And then the last one, let's look at this. I have a whole number 3 divided by the square root of 3. All right, what I need to do in this situation, okay? Remember that, let's look over at our directions again. Right here, to multiply or divide roots with the same index. Well, in this one, only one of my numbers has an index, and that is the square root of 3. So let's think about this for a minute. How could I turn my whole number 3 into a radical? What is the perfect square of 3? What is 3 times itself? 3 squared is
9.
9. So I'm able to turn that whole number into a radical. Okay? So to be able to divide radicals, they both have to be radicals. So the first thing I had to do was turn that 9 into turn that 3 into a radical. The way I did that was I just said 3 times 3 is 9. So 3 is the square root of 9. So now I have 9 divided by the square root of 3. Under my radical, I have 9 divided by 3, which is going to equal the square root of 3. Okay. I will tell you a little trick on that though. Okay. Whenever you have a whole number that is the same as the radicand, so I have a whole number divided by the square root of that whole number, my answer is going to be the square root of that number. So 7 divided by the square root of 7 is going to equal the square root of 7, because the square root of 7 times the square root of 7 equals the whole number 7. Okay? So the square root of, I'm sorry, if I had 4 divided by the square root of 4, that's going to equal the square root of 4. 157 divided by the square root of 157 will equal the square root of 157. Everybody following? Everybody good with that? So if I have a whole number divided by the square root of that number, my answer is going to be the square root of that number. Because remember how when I divide, I can undo it by multiplying. I can multiply my answer times my part and get my other part. Same thing here. Square root of 7 times square root of 7 equals my whole number 7. The square root of 4 times the square root of 4 equals my whole number 4. The square root of 157 times the square root of 157 equals 157. Okay? So if you ever see a problem, which you will in your homework, and you see a whole number divided by a radical that is that same number, you know your answer is just that radical. Okay. So let's go ahead and do this. We are going to skip activities 2 and we're going to move on to activities 3. So let me look at our time for a minute. 11:51. We've got about 14 minutes.
Wait, what would you do if there was a whole number in multiplication?
Okay, so let's see. Let's look at this one right here. So this is on page 16, right-hand column. I'm looking at 4 times the square root of 3 times 3 times the square root of 2. I'm going to set this up to where I'm going to have 4 times 3. And then I'm going to have the square root of 2 times the, square root of 3 times the square root of 2. So I'm going to put those underneath the radical. I multiply 4 times 3 is 12. Since 2 and 3 are prime factors, I know that I cannot simplify that radical anymore, so I'm going to multiply them together to get the square root of 6. Okay, so just like we did when the division ones, you would divide your first 2 numbers and then put everything under the radical. Same thing with multiplication.
No, I mean multiplication with the whole number and your radical.
Do you have an example of something? Can you give me, I'm not understanding what you're asking. So do you have a?
Well, there's no example. I was just curious, like the 7.
Oh, you mean like if I had 3 times the square root of 2?
Yeah.
Okay, so in that situation, that would just be 3 times the square root of 2. Okay, there's nothing I can do. I don't, since I'm not dividing and I'm just multiplying, I would just keep it as 3 times the square root of 2. Okay, or if I had 3 times the square root of 3, that's just going to be 3 times the square root of 3. Okay, so multiplying it is much easier than dividing it. All righty, so for homework, we are going to have activities 3, activities 4, and activities 5 on page 16. So we have our study guide, activities 3, 4, and 5. And that is going to be it on the homework. Okay, so what I'm going to do is I want you to go ahead and start working on page 16. Go ahead and start working on this. I'm going to go ahead and get these papers together ready to email you guys so y'all have got them. Let me see. If you have questions, be sure to let me know so I can help you. But what I will do is I'll go ahead and email y'all.
So the whole page?
Yes. So go ahead and start working on it now, and then you may get a good bit of it finished now and you won't have as much for homework.
Which page was it?
It is page 16.
The whole page?
Uh-huh.
All right.
Well, I guess it's not coming up on here as a whole email.
So we don't have to worry about activities 2 on page 15?
No.
I'm still not entirely like getting this. Do you mind explaining it to me again?
Yeah, let's go ahead. Hang on just a minute. Let me get this email sent real quick with the study guide, and then we'll go through it some more. We'll get some extra practice.
Wait, I have one quick question. So like on activities 3, where it says, 36 equals, do you want us to break it down so you can see our work, or is it okay if we just put 6?
No, if you know that the square root of 36 is 6, just write 6.
Okay. Wait, is it possible to have nothing under the radical as an answer?
Well, just like you just did when you did the square root of 36 is 6, your radical goes away. So if you've circled everything and everything's come out and there's nothing left, then it goes away.
Oh, okay.
Okay, I just emailed the study guide. For those of you that are needing some extra practice, let me go ahead and we'll do a couple of extra. Let's see, that's not what I want. Okay, so step 1, we said we want to find prime factorization of radicand. Step 2, I need to use the index to determine how many of each prime factor must be under the radicand to come out as one number.
That was step 3 last time you said it.
I think I in steps 1 and 2, they were both about prime factorization. I think the first one I said start with your smallest prime factor and then do the prime factorization of the radicand. I broke it into 2 steps. This time I just condensed it into 1. So it's still the same, your same process. Any other?
Like I meant like kind of explain the
Okay, well, what
the
I want to do is
lesson.
I want to write the steps out first, and then we're going to go through the numbers, okay? Because I want you to be able, if you get stuck and you're at home, when you're looking at a bunch of numbers and you don't know what to do, then you're just stuck. But if you have steps in a process and you can look back and go, okay, I found the prime factorization, now what do I do? Now I've got to use the index. So I want you to have these steps so you know when you get stuck, go look to see what step you're at. Or did you skip a step? Is there something going on so you missed it because you skipped a step? Okay, so step 3, any other numbers not grouped stay under the radical, multiply whole numbers outside of radical. Okay, so we're going to use these steps to walk through some of these things, okay? So let's say I'm doing the square root of, let's do the square root of 84. Okay, so step 1, I need to do prime factorization. I'm always going to start with my smallest prime factor. This is an even number, so I know 2. And 2 is going to be 2 times, 2 will go into 84. What is that? 42 times? Whoops, I don't want to write 42. 2 times 42. So now I'm moving down to 42. So let me write this out, okay? Do you prefer to use the ladder method or the factor trees to find prime factors?
The ladder method.
Ladder, okay. So what I'm going to do is I'm going to start with 84, and I've divided by 2. 2 will go into 84 42 times. 2 will go into 42 21 times. 21 is not even, so now I'm going to try 3, and that will be 3 times 7. Okay, 7 will be 7 times 1. I've gotten down to 1, so my prime factorization for 84 will be 2 times 2 times 3 times 7. Are you good with that so far?
Yeah.
Okay, so now we've done prime factorization. Now I'm going to look at that index. Step 2 says I need to look at my index. My index, I don't have one there, so I understand that it is a 2. So that means I've got to have 2 buddies, okay? And the way that I've taught this before, like I said, this is silly. So those of you that had me from pre-algebra last year, you already heard me say this. When I talk about buddies, okay, I say that my radicand is the house, all right? And Mama has said that if you don't have a buddy, you cannot go outside the house, right? So these 2 2s, they're buddies. So Mama lets them go outside the house. So they get to go outside, and they're coming outside as one group of 2, okay? So one group of 2 got to come out because they were grouped there. The 3 does not have a buddy. He could only buddy with a 3. The 7 does not have a buddy. He could only come out with another 7, okay? So what I'm going to do is the 3 and the 7 have to stay under the radical, but I'm just going to go ahead and multiply them back together, and they have to stay in the house. Mama won't let them go out, okay? You have to have a buddy to go outside. Your index tells you how many buddies you have to have. So let's do another number, and I'm going to get you to kind of walk me through it. Let's do, let me put a number together. Okay, we're doing a big number. You ready? We're going to do 216. Okay, we're going to do the square root of 216. So let's start with our ladder method. What is the smallest prime factor of 216?
2.
2. All right, 2 will go into 216 108 times. Okay, what's my smallest prime factor of 108?
2.
2. 2 will go into 108 54 times. What is my smallest prime factor of 54?
2.
2. 2 will go into 54 27 times. Now I've gone to an odd number, so now I'm going to try 3. 3 will go into 27 how many times?
9.
9. Okay. 3 will go into 9 3 times, and 3 will go into 3 1 time. I've gotten down to 1, so now I know I have my prime factors. And they're going to be 2 times 2 times 2 times 3 times 3 times 3. You good with that?
Yes, ma'am.
What is my index?
A 2.
A 2. So how many buddies do I have to have?
2 buddies.
2. Okay. It is 12:06. So those of you that are ready to go, you're welcome to go. If you still need to hang around for a minute, hang on, and we'll finish this one up and then we'll go. So if you're ready to go, I will see you guys on Monday. I just emailed your study guide, so you should already have it. And our homework is going to be study guide and then all of page 16. Hope y'all have a great rest of the week and weekend.
You too.
All right. Thank you. All right,
Bye.
Richard. Bye-bye. So Richard, what we did here is we've got our prime factors. We said our index is 2. So now we're going to circle 2 2s. That 2 is by himself. He doesn't have a buddy, so I got to leave him alone. And I've got 2 3s. Okay. So now with those numbers that I circled, I'm able to pull a 2 out. I'm able to pull a 3 out. And then underneath the radical, I still have a 2 and a 3. So now I'm going to multiply 2 times 3, and that is 6. And then under the radical, 2 times 3 is 6. So my answer is 6 times the square root of 6.
But how did you get 2 times 3 for the index and the radicand? Oh,
Well, it just so happened to be that way. Okay, so do you notice when I circled my 2 2s here, it comes out as a whole number 2. My 2 3s here come out as a whole number 3, and I have to multiply those together. It just so happens that I had a 2 left under here that didn't have a buddy, so he had to stay, and a 3 that has a buddy, so he has to stay. Let's look at another one that won't be the same. Let's see. Let me come up with another number. Okay. All right. So we are going to do the square root of 280. Okay. We're going to start with our ladder method, which is 280. Smallest prime factor will be 2, which will go into that 140 times. 2 will go into 140 70 times. Now, I know 2 will go into 70. Nope, not 30, 35 times. 35 is odd, so I'm going to try 3. 3 will not go into 35. I know 4 is not a prime factor, so now I'm going to go 5, and 5 times 7, then that would be 7 times 1. So prime factorization, I'm going to have 2 times 2 times 2 times 5 times 7. You good with that so far? All right, my index is 2. So that means I need to have 2 buddies. Those are the only 2 that can buddy. Okay? Those are the only ones that can go outside as one whole number 2. So they come outside as a 2, but notice underneath the radical, I have 2 times 5 times 7. None of those can buddy up. So my 2 is the only one. 2 times 5 is 10. 10 times 7 is 70. So then that would be my simplified answer. Anything that's left under the radical that cannot be buddied ends up multiplying together to stay under the radical. Anything that is buddied up and gets to come outside, if there's more than one of them, then they multiply together. Does that help?
Yes, so like the buddies, like the 2 on the outside is the result from the buddies?
So yes, this 2 comes from having one group of 2s, okay? So by circling, so basically, let's see how I can do this. Okay, so if I have 2 times the square, 2 times 2, right? Which basically, that, let me break this down. This would be 2 times 2 times 5 times 7. Or actually, I could even break it as the square root of 2 times the square root of 2 times the square root of 5 times the square root of 7. Okay? If I put them all separately, and yellow is not showing up very well. Let me change my color real quick. Okay, so when we broke that down, I could have that I could list as the square root of 2 times the square root of 2 times the square root of 2 times the square root of 5 times the square root of 7. Okay, you good with that so far? That those are the same thing. The square root of 2 times the square root of 2 is the square root of 4, right? What is the square root of 4?
2.
2. So do you see how really here I have the square root of 2 and the square root of 2? So I've got 2 2's here, which is the same as the square root of 4. So the square root of 4 is 2. Does that help you to see it better? That really when I have these right here, this is the same as the square root of 2 times the square root of 2. The square root of 2 times the square root of 2 is the square root of 4. The square root of 4 is 2. So just like if I would have the square root of 3 times the square root of 3, that equals a whole number 3, right? So if I had under the radical 3 times 3, because that is the square root of 9. Does that help? So by circling these 2 3's, it's basically saying, okay, this is the square root of 9. The square root of 9 is 3. So that's why only 1 3 comes out. It takes 2 of them under the radical, but outside it's only 1.
Yeah, that makes sense.
So the main thing is that whenever you have them under the radical, whenever you circle 2 together, if it is a square root, then it only comes out as 1, because basically this is the square root of 4. The square root of 4 is 2. Right here, this is 3 times 3, so that's the square root of 9. The square root of 9 is 3. Okay? Practice with these a little bit. If you have trouble with it, let me know. We're going to spend a little more time with it on Monday, so don't think that like this is it, okay? Radicals is definitely a more abstract concept, okay? It's something that really, it takes a little while to get it, okay? So don't stress right now. Just practice with your homework, do the best you can, and we'll practice more with it on Monday.
When is this stuff due?
So the page 16 in the study guide, those are due before class on Monday. So on Monday, those are the things to have uploaded before class.
But I still don't understand, like, the multiplying and the stuff with the square roots.
Okay, so
like,
are you still there? Or are you?
five
Okay.
to like the third to the square root of 5.
Okay, so what I want you to think about in that situation, okay? Let's pretend like I have 2a plus 3, okay? These are not like terms, so I cannot combine them. Do you remember that? That these are not like terms. So the whole number 5 and the cubed root of 5, these are not like terms. So basically this means 5 times the cubed root of 5. There's something that my phone is picking up on when I do math and I say certain problems, it thinks I'm talking to it. Okay, so basically this means 5 times the cubed root of 5. This is an irrational number. Remember when we talked about imperfect squares, imperfect cubes? That's an irrational number. This is a rational number. So because one's irrational and one's rational, I can't combine them together. They just have to stay like that. Okay? I can't simplify it. I can't make it do anything else because one's rational and the other one's irrational. So I would just have to leave it alone.
And so, like, how do you get the cubed root of 5? Because 5's a prime
You don't.
number.
There, you cannot, and that's one of those things. That's why it's an irrational number, because the only way here, and actually I'll do it on here. Let me find a calculator real quick. Let me see what's not on there. I don't even know if my son has a calculator on here. Surely so. If not, I need to put one. Okay, I guess not. So what I'll need to do is, let me just do it like this. Okay, so on my calculator, I'll turn it sideways. I may not even have a cubed root function on here. I only have square root. So let's do this. We'll Google it.
Miss Jennifer, I'm having trouble with some of the same problems on page 16.
Okay. Hold on just a minute. What is the cube root of, oh, not E, 5? Okay, so the cube root of 5 ends up being 1.7099759. So it's a number with a whole bunch of decimals that I'm not going to want to deal with. Okay, so I'm not going to worry about changing a cubed root. I'm going to leave it as a radical. Okay, so that's the reason why when we have a whole number and a radical, I just leave them the same. I mean, I just leave it as it is because I don't want to have to calculate the cubed root of 5. I don't want to have to get out my calculator, and there's not a way to do it by hand. You've got to use, I mean, I'm sure there is, but it would take a long time, and that's not something we're going to deal with. So I'm going to leave the cubed root of 5 as the cubed root of 5 because I cannot simplify it any further.
Then what do we do with the 2 5s?
This,
Multiply them?
no, this 5 is different from this 5. Okay, remember, this is like terms. Like I cannot add a plus b. I can't add them because they are different terms. 5 and the square root of 5 are different terms. I cannot combine them. Okay, so it would just stay as 5 times the cubed root of 5. That is the simplest way I could write that answer. I cannot do anything else to it because this is a whole number and this is a radical. So they have to stay separately. That would be just like if I did 2 times a. I cannot do anything to make them go together because 2 is a number and a is a variable.
So also like the cubed root of 16, when we were doing that on the classwork, it was 2 cubed the square root of 2.
Okay, so let's take a look at this. So we said that 16 was 2 times 2 times 2 times 2. Okay, so we're dealing with the cube root. I've done my prime factorization. My index tells me 3 buddies. That group of 3 comes out, that group of 3 2s, I've got my whole number 2, and then what's left is the square root and the cubed root of 2. My index is 3, so I have to make sure my index is 3 here. This is the only guy that could not come out, so he stays under the radical sign. So my answer is 2 times the cubed root of 2.
So those 3 2's put together, it's just 2.
So this would be the same as saying the cubed root of 2 times 2 is 4, 4 times 2 is 8. Okay, so 3, the cubed root of 2 times 2 times 2 is the same as the cubed root of 8. Okay, when we think about our exponents, 2 to the 3rd power equals 8, right?
Oh, so it's kind of like dividing a little bit.
Well, it's kind of the reverse, just like when we do exponents. So doing roots is the opposite of exponents. So if 2 to the 3rd equals 8, then the cubed root of 8 equals 2. Does that help?
Yes.
Okay, so basically what we're doing is it's like reverse exponents. Okay, but when we deal with an index of 3, it's different than dealing with the index of 2. When we do square roots, we're doing numbers that have an exponent of 2. When we're doing cubed roots, we're looking at numbers that have exponents of 3.
And also like problems like the square root of the cubed square root of 10.
Tell me, so nothing there's not a cubed square root of anything. Okay?
Like,
so are you talking about this?
Mm-hmm.
That's the cubed root of 10. That's the cubed root of 10. This is the square root of 10.
So the cube root of 10 plus 5 to the cube root of 10.
Okay. 5 times the cubed root of 10. You talk about that?
Yes, ma'am. How do I figure out one of those problems?
Okay. So remember we said that if we are adding or subtracting radicals, and we have a radical that the index and the base have to be the same. So with this one, My index is 3, and then my my radicand is 10. On this one, my index is 3, my radicand is 10. Those are the same. So if those are the same, then I'm going to look at what numbers come before them and add them. This is the one that I don't have a number in front of this one, and so I'm going to write a 1, because anything times 1 is itself, right? So by the understood number in front of that is 1. So now what I'm going to do is I'm going to add 1 plus 5. So I only add the whole numbers. So 1 plus 5 is 6. Then I keep the index and radical the same. I don't change it. I don't do anything to it. I keep it exactly the same as it is. So I only add the whole numbers in front of them. And then as long as the index and radical is the same, then it's going to be the same in the answer. Does that help?
Yes.
Awesome.
Miss Jennifer,
Yes.
I have to go get ready for my next class. Would it be okay if I emailed you my questions about
Absolutely. Absolutely. I've got a class at 12:40 also, so I'll be teaching till 12:25. So if we need to hop back on a Zoom at the end of the day, let me know and I'm happy to.
I don't know if I can because I have PE and that's gonna last like till 3 or 4.
Okay.
So.
Okay.
But
Yeah.
I'll email you with my questions.
That'll be just fine.
Okay,
That'll be just fine. Okay. Thanks, guys. All right. Are you good, Richard?
One more question.
Sure.
It's about the multiplying them.
Uh-huh.
The square, how do you multiply square roots?
Okay. So if, let's say I have the square root of 2 times the square root of 3. All right. What I'm going to do is I'm going to draw a radical and I'm going to put 2 times 3 under the same radical. So all I've done is I have put these together under the same radical, and then I just multiply them together. 2 times 3 is 6.
Oh, makes sense.
Okay. And so I know that can't be simplified. Let's say I have the square root of 2 times the square root of 6. I'm going to put those under the same radical. So I'm going to have 2 times 6. So what is that going to give me?
Square root of 12.
The square root of 12. Now I can simplify the square root of 12. So now I've got to think about what are my prime factors. I'm going to do my ladder method with 12. 2 will go into 12 6 times. 2 will go into 6 3 times. 3 is prime, so I know I'm down to 1. So now I've got 2 times 2 times 3. Okay, so 12, prime factors, 2 times 2 times 3. My index is understood to be 2, so I know I have to have 2 buddies. So the square root of 2 times the square root of 2 is the square root of 4, so I know the square root of 4 is 2. That's why only that 1 2 comes out. This guy's left under the radical, so he has to stay. So every time I write an answer that is a radical, I have to check and see, can it be simplified? The only way I know if it can be simplified is by putting it as prime factors and seeing what can be factored out.
And one more question. I promise this will be the last one.
Oh, it's fine, honey. Whatever you need.
So it's 10 times the cubed root of 16 divided by, or any kind of like, I guess, symbol, 5 times the cubed root of 4. So,
Okay, like this?
Yes.
Okay.
Say you tried to like add those.
You cannot. Remember, our rule is that these have to be identical, and they are not. So I cannot do anything with that. Okay? There is nothing I can do. I can't divide anything on here because my first thing to check is the index the same? Yep, they're the same. Is my radicand the same? Nope, they're not. So I cannot do anything. The only time I could do something is if they were the same. So if I had 10 times the cubed root of 16 divided by 5 times the cubed root of 16, now they're the same. So I could do 10 divided by 5 is 2, and then I keep my radical. So in that sense, I could do something, but if they're not the same, I can't do it.
Because this problem was right here on the classwork, down like at the very bottom, the one above the very last one in the class.
Oh, and you know what? Hold on. If the index is the same, I'm sorry, I'm thinking of addition and subtraction. Let me go back to this real quick. The sample, the 10 times the cubed root of 16 divided by 5 times the cubed root of 4. Multiplication and division, only my indexes have to be the same. So in this situation, I'm going to have 10 divided by 5. And then I'm going to have times the cubed root of 16 divided by 4. I'm going to put these together under the radical if my indexes are the same.
That makes sense.
Okay, so 10 divided by 5 is 2 times the cubed root of 4. So in the one in the book, we have 15 times the cubed root of 16 divided by 3 times the cubed root of 2. Is that the one you're talking about? Okay, so now what I'm going to do is I'm going to have 15 divided by 3. Those are both whole numbers, so I can do that. Then I'm going to have the cubed root of, I'm going to put 16 divided by 2 under here. So 15 divided by 3 is 5, times the cubed root of 16 divided by 2 is 8. Now I've got to simplify here. This is going to be 8 is 2 times 2 times 2. So now I've got 3 2's under there. Those are going to have to come out. So now I had a 5 already. My 2's that came out, I need to multiply those together. So my answer is the whole number 10. So since the cubed root of 8 equals 2, I already had my 5, so and I multiply them together. I'm sorry, I made that mistake. I told you you couldn't combine them, and you can. When you multiply and divide, you can put them under the same radical sign. When you add and subtract, you cannot.
I'm still kind of not picking up on this.
What I want you to do, what I want you to do is I want you to practice with the homework a little bit. I want you to look back through the examples. I want you to think back through everything. And like I said, on Monday, we're going to do it again. Okay? And so what we can do is on Monday, it may be that after you've kind of worked with it, it may be a challenge. You may have to wrestle with it a little bit as you're doing these. Look at... Let's go ahead and look at activities 3, where you have the square root of 6 plus the square root of 6 on that left-hand column. Do you see that?
Is that 6?
Let's see, 1, 2, 3, 4, 5 problems down on the left-hand column of activities 3. I've got the square root of 6 plus the square root of 6. Do you see that?
Mm-hmm.
Let me pull up, I can pull up my paper real quick. All right, this one right here. When I'm adding, my index and radical has to be the same. What numbers do I understand are in front of, what are the whole numbers in front of the square root of 6?
2.
No, what whole number, what number times itself, or what? So the understood index would be 2. Okay, that would be part of my radical. But what is my whole number that's in front of that number? It would be a 1. Because 1 times the square root of 6 is the same as the square root of 6.
So the square root of 6 plus the square root of 6 is 6.
So what I'm going to do is if I have the square root of 6 plus the square root of 6, I understand that the whole number 1 is in front of both of them. So I'm going to add my whole numbers. 1 plus 1 is 2. Do you see where I got the 2? Okay, and then I keep my radical the same. So look at this one right here. What am I going to add?
The 3 and the 2.
3 and 2. What's 3 plus 2?
5.
5. And I keep my radical the same. Look at the next one. What am I going to add?
2 and 5.
2 and 5 is
7.
7. And I keep my radical the same.
So how can we keep the radical the same? Is it just the way it
That's
is?
the rule. That's just the rule. So that's what, and when we, on page 15, halfway down the page, it says to add or subtract roots, the radicands and indexes must be equal. Add the numbers immediately to the left of the radical. If there is no number, treat it as a 1. That's what we've done. And then it says if the radicands or indexes are not equal, the roots cannot be added or subtracted. So your radicand stays the same. You only add the whole numbers, okay? You cannot add radicals, okay?
That's kind of all I. Oh,
Go ahead.
that was kind of all I had a question about. And I was wondering if you could maybe go back up so I could like write like to the top so I could write down like, or like the page you were explaining to, like explaining it on.
So from the textbook
No, ma'am, the other page,
or the one I was writing on?
the one you're writing on.
Okay.
Because I wanted to kind of write down, like I just kind of wanted to copy it over. Just
Was
so
it this one?
Yes.
Okay, what I can do is I can email you this.
Okay. Could you email me that entire page?
Yeah,
Thanks.
yeah, I'm gonna share the note. Let's see, and we're gonna Gmail it. And then, okay, what is your email address?
Hobbs7788@gmail.com.
There you are right there. And this is notes from Algebra 1. All right, they are on their way to you. All righty, very good. Well, as you work through these, if you have trouble, let me know, okay? And then, but like I said, we're gonna keep working on Monday. We're gonna review everything again, and we'll keep working on it, okay? All righty, good deal. Thank you for asking questions, and we'll work through it, okay? We'll keep working till you get it.
Bye.
Okay, bye, hun. Have a great weekend.
You too.
Thank you.